Thank you, Nico. So, Ignacio told me I wasn't using the board. I'm not used to this system, so now I will have more space. Okay, so just as a summary, we had our path order exponential of x nu plus yi phi I. Okay? And what I showed you in the previous lecture was that if I impose that equation, so I transform this guy into symmetry, we ended up with this equation. And I'm going to write it slightly differently just to avoid confusion. So this comes from the variation of a mu. This comes from the variation of phi I. And what I said was that, and this is a standard technique, and you should maybe memorize it. Every time you have an equation, you look for auxiliary equations that come from projecting that same equation into whatever you like. So this is like finding simpler equations that are implied by the original equation, and then first solve the simplest ones, and then you go back and try to solve the original one. But it's a very standard technique. It's also true with differential equations. Okay. So what I showed you was that this, if this is 0, then it must be true that x dot squared was minus y squared. And I didn't write it in this way. I wrote it with a vector n, just because I chose to write y as x dot times n. But really, that's the condition. Okay, just maybe this is simpler. So this tells me basically that x dot has to be time limited, because this vector is a vector in R6. Its norm is always positive. So that's the idea. Okay, and then I can always parameterize the curve such that the tangent vector is unit. That's a choice of parameter. So I can put x dot squared equals to minus 1 and y squared equals to 1. Okay? That's just a choice. If this is not true, if this is different from 1, just redefine what the dot means. And you set it equal to 1. Okay? So it's as simple as that. Okay. So the next step is, well, now we have this, we go back. Remember, our curve was a straight line, right? Well, if I now take the derivative of this equation, so I take a dot, okay, I will get so I'll just skip the details, but x double dot mu will have to be 0. Okay? So this is really a straight line. Okay? And this just comes from taking the derivative here. Okay? You get a x double dot here, you get y dot, and then y dot you can get from this condition. So basically, it tells you that x double dot is 0. So this means that I can choose x dot to be the curve tau 0, 0, 0. So that's a straight line pointing in the time-like direction with unit vector 1, right? So the tangent is 1, 0, 0, 0, which has norm minus 1. We're all mostly plus here, right? Any mostly minus people can go out get out of the group. So, and then y has to be also unit vector, and it has to be a constant unit vector. So I can choose it in whichever direction I want, okay? So I will choose this to be 0, 0, 0, 0, 0, 1, okay? So now, the last part is, what are the epsilons that I can put here and preserve some supersymmetry? Ah, by the way, so when I talk about supercharges, I mean how many possible epsilons there are. It's a matter of language. This is the same as with bosonic symmetries when you have Nether's theorem. There's one conserved charge for each free transformation parameter that you have. Right? So angular momentum, you have 3 angles. SO3 can be parameterized by 3 angles, so you have 3 conserved charges. Right? This is the same. Supersymmetry, you have, in this case, you have 32 possible parameters, so there's 32 supercharges. Those 32 parameters are this vector, epsilon. This is a spinner with 32 components. Okay? So now I want to know, can I keep all the 32 components arbitrary? In which case I will preserve 32 supercharges, or I need to set some of them to 0 or equal to each other to preserve supersymmetry. So then all I need to do now is plug in this back here. So I don't know if you noticed, but we've been, when we started, there were 2 unknowns. Yes?
This x mu is, this line is
It's time-like, yes.
Yeah.
Because this. Well, it has to be negative norm. When we started, we had 2 unknowns. One unknown was the curve, and the other unknown was the epsilon. We had 2 unknowns. And so we wrote the equation, and then we found some integrability conditions for the equation. And we constrained the curve to be a straight line. We took the derivative, blah, blah, and so we constrained the curve completely now. We know it's a straight line in the time-like direction, but now we still need to know what are the epsilons that are allowed. But if I plug that specific, very specific curve in here, I get gamma 0 plus gamma 6 times epsilon equals 0. Okay? Which I can write as 1 minus gamma 0, 6 epsilon equals 0. Or okay? So you agree if I put x dot equal to 1, 0, 0, 0, all I get is gamma 0 here, right? And I get gamma 6 here.
Okay.
Yes?
So there is if you call it gamma, I understand why you're calling it gamma 6, but then you have a clash with the notation. What's the gamma in gamma 4 in the 5 space dimensions? You chose that the gamma 6 is the last one, right? Because I goes from 1 to 6.
Yes.
But what's going to be gamma 4? Gamma 4
okay,
is
yes.
the second
Thank
one.
you. Yes, yes, yes. Thank you. Thank
We
you.
could call it gamma 9.
But, yes. Oh,
Yes. Okay.
And then, okay, I don't know what to do here. Did everyone understand Brita's point? Yes? These are 10D gamma matrices, so they go from 0 to 9. But then I changed from 0 to 9, I changed from 1 to 6 for the other one, so I messed up the notation. But yeah, so okay, let me be more careful then. So this would be gamma 9, I guess. Yeah, thank you, Brita. Gamma 9 because the sixth scalar, the last scalar, is the ninth component originally in the 10 dimensions. Okay, now this equation has how many solutions? We are in a vector space of dimension 32, right? So this matrix gamma 0, 9 is 32 by 32. It squares to 1. You can easily show that it squares to 1. So its eigenvalues are plus or minus 1, right? And then supersymmetry is telling me you have to choose the eigenvalue equal to 1. How many eigenvectors have eigenvalue 1? How can I know? Well, it happens that this guy is traceless. You don't need to know this, but trust me, you can show, this is just from Dirac-Clifford algebra, the fact that the trace of gamma 0, 9 is equal to 0 tells me it has to have exactly the same number of positive and negative eigenvalues. Otherwise, the trace could not be 0. Do you agree? Because the trace is the sum of the eigenvalues. I know the eigenvalues must be 1 or minus 1 because the matrix squares to 1. So the eigenvalue squared is always 1. So there have to be 16 eigenvectors with eigenvalue 1 and 16 with eigenvalue minus 1, right? So 16 eigen plus 1, 16 eigen minus 1, and then supersymmetry is telling me you can only choose those that have eigenvalue 1. If you choose the ones, the spinors that are eigenstates of gamma 0, 9 with eigenvalue 1, then your Wilson loop will be supersymmetric, will be invariant under this supersymmetric transformation. Okay? And because 16 is half of 32, we call this half BPS. Okay? Of course, you can now think of generalizing this and finding more complicated curves. Okay, for example, you can put a straight line here. Okay, and you can put some latitude circle in 3 directions. So let's say cosine theta 0, where theta 0 is a free parameter, or sine theta 0, cosine tau, sine theta 0, sine tau, cosine theta 0. Right? If I put theta 0 equal to 0, I recover this. But now I have a more general, and it's not constant actually. It's a circle. It's a latitude. It's called the latitude Wilson loop. And you can show that if I choose that curve, I will find solutions, but they will be quarter BPS because in addition to this, there will be another projection that I need to apply an epsilon in order to solve. So the equation will change. It'll no longer be this. It'll be different. Sorry, no, this part is the same, but the algebra will change because now it will no longer be constant or whatever. So now I can let my imagination go rogue and try to find the most general Wilson loops, and I think they are actually classified. All the BPS Wilson loops in N plus 1. So I can do 1/2, 1/4, 1/8, and 1/16, and I think that's where it stops. Okay, how many? That means how many supercharges are? How many free components that does epsilon have? That's the number of supercharges that we have, and you count from 32 down. Okay, great. So now I'm gonna give you a fun fact. You can show, and this is a general argument. Notice, by the way, so this is a technicality, but the epsilons that are preserved are constant. The theory has epsilons that have a linear dependent on x as well as part of the supersymmetry. So 16 are constant and 16 are linear. Of the 32, 16 are linear in the coordinates of x mu. These are all constant, okay? So that's what we call Poincaré supercharges, because basically they're the same as they come from the Poincaré algebra and not the superconformal part.
Are there 3/8 BPS?
3/8, that's a good question.
Yeah, I don't know. That's what I'm asking.
No, I don't know if there are. I know in ABJM there are 1/3.
Any reason why not? Okay, maybe there is a reason why not. I just don't know. Sorry, I was just curious.
If you want to get 3/8 BPS, you would have to find a projection that has an uneven number of eigenvalues, right?
Yes.
Which I guess you could do that.
If you have 1/4, that's already.
No, 1/4 is easy because all you need to do is find some other matrix that commutes with this one, and it's two successive projections of 1/2. But if you want like a different fraction, you would have to project. By the way, every projection that you apply must commute with each other, otherwise, of course, you know this from quantum mechanics, right? You can only diagonalize things that are commuting. But to Brenner's point, you would have to find maybe some linear combination of gammas and project and use that as a projector. This happens in ABJM. So in ABJM, it naturally comes out as 1/3, 1/6. You have 24, so you can divide by 3. But in ABJM, because the target space has 24, so the 24 supercharges come from a 32 component spinners that you project onto 8 plus 24. So something like, so the target space, ADS4 plus CP3, is actually 3/4 BPS. From type 2A has 32 supercharges, and the background has 3/4. So there you have an example, maybe not in the Wilson loop context, but in the supergraphic context. Okay, so fun fact. The VEV of the straight half BPS Wilson loop is, what do you think the expectation value of this Wilson loop is? When things are too symmetric, things get boring, right? 1, the exponential of 0. Okay, and this is because the supercharges that we preserve are Poincaré supercharges. So you can make general arguments that that's always the case. Okay, because Poincaré supercharges are related to translations, and you can make the case that it has to be 1. So what do? It's kind of boring. You can go find some other Wilson loops that are supersymmetric but don't have trivial expectation value. The 1/4 straight line will also have trivial expectation value, or we can do a trick. Okay, and the trick is the following. If we go to Euclidean signature, so in Euclidean signature, there's no time direction, right? So this straight line is just a space-like line, like in any other direction. So there's no time-like condition anymore. In this case, we can map the straight line to a circle. With a conformal transformation. Okay? Have you seen this done?
You will get a byfactor, right?
Yes, because it's a conformal transformation.
But this is the new dynamics. The new dynamics is the byfactor that appears because of the conformal transformation.
The new dynamics, you mean?
Well, when what you do actually is change the byfactor and this give you other thing that is not 1.
Yes, but it's not dynamic though.
Ah.
You have to be careful. There's no metric.
Yeah,
There's no metric degrees of freedom here.
Yeah, it's digital.
Okay, but yeah, I will. This actually comes back to your previous question about gauge transformations.
Oh.
Because something funny happens here. So let me just explain why the circle is the same as the line. Do you guys know that? No?
With the points identified? That's
No, it's just a conformal transformation from the plane to the sphere, and you can map a circle to a line. And actually, maybe I'll do it. I'll do it because you don't find this in too many books or papers, but it's a nice exercise. So if I take my plane xy and I take a circle, and take a dot, some point here, and I define small x as 2x 1 plus x squared plus y squared. So, okay, now we'll write. And then uy as I don't even understand my own handwriting, so that's the problem. Minus 1 plus x squared plus y squared divided by 1 plus x squared plus y squared, okay? You can show that a straight line in the x, handwriting is horrible. Right, so you can show that x squared plus y squared is equal to 1, okay? If you live on a line in the x, in the large X or capital X, capital Y plane. I think that's correct. Well, I can show you my, and then you can explain it to me. All right. Okay. Let's take it in faith. I'm confused because I don't know which one's capital Y, capital X, and all that stuff. But anyways, this is the standard stereographic projection from S1 to R1. Okay. So what you do here is that you map a point here to a point here. Okay. The picture is this. So this point on the circle corresponds to this point on the plane, on the line. Okay, that's the map. Then you can figure out if this formula is correct or not. Okay, but this is the map. Starting from the North Pole, you trace a line that goes through the point in the circle, and then you intersect the line, and this point gets mapped to that point. And then you can see that by moving this point, I will map the full real line. And the only point that's left outside is the North Pole, which will be mapped to the sort of parallel line that never intersects the x-axis.
That's a circle or a sphere?
You can do it for a circle, the sphere, or whatever size sphere. This is just a standard stereographic projection. In this case, it's a circle, and the point I'm making is that the straight line that I'm using to define my Wilson loop, if I switch to Euclidean signature, which has its own problems, okay? Trust me, when you do supersymmetry, you cannot just take the signature from Lorenzo to Euclidean that easily, but people do it anyways. I'm saying that this line, which is my Wilson loop, can be mapped to a circle.
Can you repeat what's happening with the North Pole?
The North Pole is not, so this, to be very technical, this is a homomorphism from the circle with the North Pole removed to the straight line, to the infinite line. And the North Pole is not mapped to any point. That's why they call it the one-point compactification of the line. You take the infinite line and you add 1 point and you get a circle. And what they mean is just this picture. That's what they mean. Okay? Oh, well, this picture and the correct formulas. Okay? But they mean something very concrete and down to earth. They don't mean some. No, well, mathematicians can do it as complicated as they want. But
This picture, X,
so
X and Y, the capital.
I guess this. No, this is. No. Sorry. Now I understand my handwriting. Sorry. So this is X. This is X. This is X. Sorry. And this is X. I made a mistake there. Yeah. Thank you. Sorry. So X is this coordinate, and XY are those. So this is. Yeah. Thank you for. That's what I mean. Now the formulas are correct. Thank you. Okay. You can. This is just algebra. Take this guy squared plus that guy squared, and that will give you 1.
To remove that point,
Which point?
the North Pole,
Yes.
you don't lose information.
Oh, yes.
That's bad.
No. Well, it can be if you don't keep track of it. Yes, it can be bad. Let me be clear. I'm not saying that the straight line is exactly the same as the circle. I'm saying that there's a conformal transformation that maps them, but that conformal transformation has a singularity and 1 point. Okay. So if you want the transformation to be regular everywhere, you're not mapping the circle to the line. If you allow one singularity, then you do this map. Okay. But it's localized in 1 point. And actually, that's my next comment. Yes.
The x-axis should be under the cycle, right? To be the rest of the cycle.
No. This is the one where the axis goes.
So you will not from below, up from below. Because inside the circle you will not get there, right? Because the projection. Well, I mean, you are right.
No, if you want x, if you
Yeah,
take
it's
x
in the
to be
middle.
smaller than 1,
Yeah, it's coming in the middle of the cycle. Yeah.
this is negative. And why negative? I'm sorry. Yeah, it's this. No, this is more.
No, you're right. If x is smaller than 1, big X is smaller than 1, then you map with you continue the line and you map to the part of the circle that's below the.
Yeah, you're right. Yeah. Exactly.
You mean this?
No. Just keep lowering X, big X.
This.
Yes.
Yeah, you're putting inside instead of putting up.
So this point is mapped to that point.
Yes, exactly. Yeah. But this one is the picture is the axis below. That's why I was so confused.
Yes, I mean you could do the same, but you could
Yeah,
do
you
it.
have the same. Yeah.
Yes, of course.
Yeah.
But it's just some
It's the same.
some variation of these formulas. Yes. Yes, I chose this because these are easier. The case you mentioned is just that you need to translate all the coordinates and
Yeah.
it's easier. Anyways, let me get to the important part. I told you at the beginning that anyone's force to Berry-Mills is a conformal theory. It's a conformal field theory. It means that among its symmetries, it's conformal symmetry, right? So what does that mean? It means that if I compute some observable and I apply a conformal transformation, I should get the same answer, right? That's what Poincaré symmetry means, or that's what Lorentz invariance means. If I compute some physical quantity and I do a Lorentz transformation, I expect to get the same quantity, the same answer. Because the theory, the path integral, the Lagrange, and blah, 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 was Lorentz invariant, right? So now I have a conformal field theory. So I expect that if I compute some observable it will be invariant under conformal transformations now. So now I have a Wilson loop. It has a trivial expectation value. It's a line. I'm telling you, okay, I will map the line to the circle, but the map is a symmetry of theory. It's a conformal transformation, so you would expect the expectation value of the Wilson loop to be the same. That would be reasonable, right? But it doesn't. It's not. So even though this is a symmetry of the theory, the web of the Wilson loop changes. So I mean, now that even though this was 1, this is different from 1. So how can that be? There seems to be a contradiction, right? Because I took the same observable, applied a conformal transformation, and got a different answer. Then it's not really a symmetry of the theory, is it? Right? And the point is the subtle one, which is precisely what Matthias was alluding to. The transformation is singular at infinity. Okay? So that makes things more fun. Usually, when you compute expectation values, you put boundary conditions to your path integral, so the fields have to go in one way or the other, etc., etc. But if I do a transformation and the transformation is singular, that would change the boundary conditions at infinity. So I actually changed the observable. Like it or not, my conformal transformation was not so innocent. Okay, and this is related to your question about gauge transformation. The same happens with gauge transformations. So if I have you're taught that gauge transformations don't change anything, but if my gauge transformation is what we call a large gauge transformation, so that the gauge parameter survives at infinity, things can get fun, okay? And it's actually the reason why, for example, gravity in 2+1 dimensions doesn't have any local degrees of freedom. There's no gravitons in 2+1 dimensions. All solutions to Einstein's equations in 2+1 dimensions are diff equivalent. So there's no local degrees of freedom, but if you allow diffeomorphisms to survive at the boundary, then you will get inequivalent physical configurations. Okay? So this is something similar. It's of course in a different context. This is not a gauge transformation. It's a global symmetry, but still, okay? It's a global symmetry that was singular, so it's not a surprise that things change. And one can see this when one does the perturbative calculation is that the propagator for the gluons, because remember we're computing an expectation value of some exponential of gauge fields, blah blah blah. So if you expand this as a power series, you get a bunch of correlation functions of gauge fields, right? 2-point function, 3-point function, etc., etc. And you need to use the propagator, Feynman propagator to compute the correlation functions, etc. And what you see is that when you apply this conformal transformation, the propagator gets a total derivative. Okay, so in one case it's 0, and the effective propagator of a mu and phi. Okay, so the scalars and the gauge field compensate. In this case, you get a constant term instead of 0, and that you can integrate and get a non-trivial there. So I will give you the answer. There's different methods. So you can do it by brute force or by a technique that's called supersymmetric localization, which I'm not going to explain, but it relies on supersymmetry. Okay, so it only works for supersymmetric observables. That's why one of the reasons we're focusing on this. So you get the expectation value of the circular loop is, get this right, 1 over n. You get a generalized Laguerre polynomial of lambda over 4n. And here you get, I said I was going to use that one, I'm not using it. I think that's correct. Okay? So you get a polynomial in lambda over n times the exponential of 1 over, yes. I'm missing a lambda. Yes. Okay? There's no way you can see why that's the answer at this point. No way, you have to trust me. Okay? The main message is that because it's supersymmetric, I can invoke some very powerful techniques and compute things exactly in the parameters of the theory, which are the top coupling lambda and the rank of the gauge group. Otherwise, I have to resort to perturbation theory, and I'd have to do it order by order in Feynman diagrams, etc. Okay? But because it's supersymmetric, I can wave this magic wand and do this. Originally, they didn't do it with the magic wand. The magic wand appeared in 2008. But previous to that, they did Feynman diagrams, and they noticed many cancellations in the diagrammatics, and then they managed to find the pattern and exponentiate the full Feynman series, and they got this. Okay? Now, why is this interesting? Well, it's interesting because now I have an exact result. And now I go back to the first lecture, ADS-CFT. ADS-CFT tells me that this theory, n equals 4 superring mills, has to be equivalent to type 2B string theory on ADS5 versus 5. What that means is that whenever I compute in one theory, there must be some dictionary that I can do the same computation in the other theory with completely different variables and language and math, but the answer should be the same. Okay, so it should give you the same answer. Now, I also mentioned that this dictionary is better understood when the gauge theory, so this theory is very, very strongly coupled, and n is very, very large. Okay, it's very quantum and strongly coupled. And then the string theory is weakly coupled, and in the point-like limit, it's a classical gravity, right? So it's just fields in ADS. So in that limit, we can understand things quite well. So if I take large n here, so remember the truth limit was large n fixed lambda, and then large lambda. So if the first limit one, large n fixed lambda, I will get this, and then there are corrections of order 1 over n squared, and that's the first modified Bessel function. This is in Wikipedia. This is Wikipedia. You go to Wikipedia, generalized Laguerre polynomials, large n, when you have lambda over n times the exponential, blah, blah, and you get the Bessel function. Okay? Actually, we can do this full series exactly. So there's Bessel 2, Bessel 4, whatever, I don't remember. And then, for large lambda, this becomes okay, and then I get corrections of order 1 over square root lambda. So this is large n fixed lambda, and then large lambda. And then again, this is Wikipedia. Go to the Wikipedia page for the Bessel functions, and you will find this approximation right there. And you've probably seen it, right? So the Bessel goes like an exponential, and then some power of actually I think it goes like 1 over the square root of the argument. And then you count the powers of lambda, you end up with 3/4. Okay? So this is the result for the expectation value of the circular Wilson loop in the 'T limit. So large n, large lambda. So now we go and look at the dictionary. The ADS-CFT dictionary. What does the ADS-CFT dictionary tell me? Okay. ADS-CFT is a proposal that relates two theories exactly. So that means that there has to be an entry in the dictionary for every single observable in both theories. Okay? So the typical observables in a Gates theory or in a local quantum field theory are local correlation functions of operators, right? And that part of the dictionary was the first part that they figured out. How to compute correlation functions of local operators in the Gates theory using subgravity fields in ADS. Okay? And that's the famous Pfefferman-Graham expansion, and you get the delta plus, delta minus conformal dimensions, etc. Okay? That's how you compute correlation functions of what are called conformal primitives. The second input in the dictionary was how to compute Wilson loops, the expectation value of Wilson loops. And the dictionary is as follows. So remember that my Gates theory lives in R4, but I will think of R4 as the boundary of ADS5. Okay? And here live the fields of n=4 super young Mills. Okay? And here I have type 2B string theory. Okay? And what the dictionary, and then of course I have also an internal space which is the S5. Okay? But that's not going to play a role in what I'm going to do. What does the dictionary say? The dictionary says, do you want to compute a Wilson loop in n=4? Okay, draw the curve that you're looking at, right? So in our case, it's a circle. Right? Now interpret that curve as living in the boundary of ADS, and then try to find the minimal surface that we interpret as an open string in ADS, such that the surface pinches the boundary, the curve at the boundary. So this is my Wilson line, or my Wilson loop. And then this is the worldsheet in ADS5. The string actually lives in ADS5 cross S5. But you can start to picture how you geometrize this SO6 now. The SO6 now corresponds to isometries of S5. But for the Wilson loop, remember the one we're focusing on is 0, 0, 0, 0, 0, 0, 1. That corresponds to a string that is fixed at the north pole of the S5. So it's not going to play a role. But if the Wilson loop actually, this curve yi dependent on tau, that would be geometrized as some curve in S5. So in this case, that curve has shrunk to a point, so we can forget about it. So now the surface only goes into ADS5, and it's a point in the S5, so it's fixed. Okay, that's the dictionary. How I cannot prove it. Okay, I can argue how you get it. You do a deep ring construction in flat space with open strings, and then you Higgs one of the modes to. When you take one brane, you have n plus one branes all together in open strings, and then if you separate one brane, there's one gauge field that becomes massive, and then so that's like a Higgs mechanism, and then you take that to infinity, so it becomes infinitely heavy. So that's the infinitely heavy probe that I used to define the Wilson loop. Okay? So then what you're, yeah, that's a picture. So you get an open string that stretches all the way from the deep rings to infinity, and okay, actually, yes. Okay, and then you do the usual Maldacena limit where the deep rings back reacting to the ADS5 geometry. It's a complicated argument, but that's basically at the heart of ADS-CFT. Okay, so that's the dictionary. So you need to buy it for now. Okay, actually I'll give it to you for free. Okay, next time it won't be yours. Yes.
There's a special reason to set the string at the north pole instead of any point of the circle.
No, it's a fixed point in the sphere. This just depends on how you oriented your coordinates. So what I'm doing is I'm identifying the R6 where the scalars lived. Remember there were 6 scalars? I'm identifying as the R6 the embedding coordinates of the 5 sphere. Okay, so I chose the vector 0, 0, 0, 0, 0, 1. Okay, in embedding space that corresponds to the north pole of the sphere. So the 6th axis. But again, it's a choice because I could have put 0, 1, 0, 0, 0, or actually I could have put 1 over square root 2, 1 over square root 2, whichever point I want. The main point is that it's fixed. Okay, by the way, I forgot to mention, I talked so much about symmetries. I told you the symmetries that are preserved by the straight line, right? Remember I told you it's SO2R cross SO3? So the SO3 was easy, and 2 of the SO2R transformations were also intuitive translations and rescalings. And the SU4 or SO6 we didn't touch. Now we broke it. The moment we chose some direction in this vector n or this vector y, we broke the SO6 down to what? If I'm in an R6 and I fix one direction, how many SO6 transformations leave that direction invariant? In SO6. SO5. Right? So my Wilson loop broke the SO6 down to SO5. Right? So that was the price I paid, but I gained 16 supercharges. Right? So that was, and I gained the magic wand because it's supersymmetric. Okay. Good. So in whatever time I have left, I'm going to try to show you this calculation. Okay, so does everybody understand the prescription? I'll go in a second. The prescription is find the minimal surface, so the minimal area surface in ADS5 such that it pinches the circle at the boundary. And then compute up. So I forgot the big part. The Wilson loop will be e to the minus, I forgot, let's say number one. So it'll be the area of the worksheet. Okay? I forgot the main punchline. So this is the actual dictionary. So find this surface, extremize the area, that's an Euler-Lagrange problem, right? And then compute the area of the minimal surface, and that will be the expectation value of the Wilson loop in the dual field theory. All right? Sorry, Johan.
This is special for the circle, or
No. This prescription is general.
so you can draw any.
Yes. So any contour I write here, I will find the minimal surface, and then I will do
This
this.
straight infinite straight line is true.
Sorry?
This infinite straight line.
Yes, and actually you can show that, yes. So this guy, the minimal surface is this, and it has 0 area. This guy has negative area. I'll stop here. Actually, I'm not sure if I'll have enough time to finish this, but
But the second one is not obviously.
sorry?
The second one.
It's the same one. So this is a straight line, which I map to the circle by the conformal transformation. So I should see the fact that one has vev equal to 1 and the other one has vev different from 1. I should also see in this picture.
But it's a Wilson loop.
This is a Wilson loop in the sense that, no, technically it's not a loop. So if I'm being literal, it's not a loop, but it's still gauge invariant because I only allow those gauge transformations that die at infinity. So this is something that I mentioned at the very beginning, right? So the fact that it's closed, it's so that I get a gauge invariant. So the trace cancels the two factors of the Wilson loop. But the other way to do it is to say that the curve goes to infinity and that the gauge transformations die at infinity. So, okay, so let me see if I can do this calculation rather quickly. Yes?
If you did the straight line with different boundary conditions, you will get the same result.
Come again, if I do the straight line,
The straight line with different boundary conditions.
what do you mean different boundary conditions for the string?
Yeah, instead of Dirichlet, what mu one with the boundary.
Well,
With a mu.
that's a trick question because that's a trick question. Dirichlet and Neumann boundary conditions are subtle to define here. If you were talking about fluctuations, deformations of the surface, then I could give a precise meaning. But for the classical configuration, this.
I mean the safety, right? The Wilson line is the safety in the conformal theory. You fix both boundaries at the infinity and the infinity
Yes.
to 0 and the fluctuations are 0, so that you don't have gauge transformations in the boundary.
No, wait.
You're
Throwing in too many words. So in the gauge theory,
Yeah.
my Wilson line is infinite.
Yeah.
So I ask that the gauge fields and all the fields in my theory die at infinity.
Yes.
And in order to preserve that boundary conditions, I cannot allow gauge transformations that break that. So all my gauge transformations must die at infinity. There's no boundary here.
No, wait. Okay. Yeah. Infinity.
An infinity, yes.
But if you didn't ask this, maybe you will get.
Oh, for sure. Yes. But I'm not. Yes. But I don't know how to define the path integral with yes. Of course, I could do the conformal transformation from the line to the circle, or I could change the boundary conditions in the line. Yes. But one is easier than the other.
All right.
Okay. So we're gonna have to go fast. So does everyone know what ADS space is? No? So ADS is a space that can be defined. It's not the only way to define it. The same as you define a sphere. So the sphere S2 is defined as the locus in R3 such that x squared plus y squared plus z squared equals to 1, right? You can define the fourth sphere in the same way, just add one more dimension. So the 3 spheres embedded in R4, the 4th sphere in R5, etc. So the Sn sphere is embedded in Rn plus 1. If I take that same equation and I put a few minus signs in front of some of the coordinates, instead of being all plus, I get what's called the anti-de Sitter space or de Sitter space, depending on how many signs I change. Okay? That's it. Now, of course, it's a very violent thing to do. The space is no longer compact. So instead of getting a sphere, you get something like it's like a saddle, horse saddle. This is the same as, think of the circle versus the, what's it called? Hyperbola? Hyperbola. Okay? Both the circle and the hyperbola are defined as some implicit equation, quadratic equation in R2. Right? They only differ by a sign in front of y squared or whatever. It's the same here for ADS space. So if you do that, and then you can compute the induced metric on this surface, you will find there are coordinates where this thing looks like this. And these are the coordinates that are adapted to this picture here. So this will be R4, and then I have some extra coordinate that I call z. Okay, and this is 1 over z squared. And then I get here dx squared plus dy squared plus, actually let me start with z. Let me do it like this, dz squared plus d vector x squared. Okay, so this is R4, and then there's an additional fifth direction, z, and then the metric is 1 over z squared times the flat metric. Okay, and then the boundary is z equals 0. Right? So if I put z constant, I get a bunch of planes, R4. So at each constant z, I get R4, R4, R4. And then the boundary theory lives in the last plane, which is z equal to 0. Now, many of you noticed this has a singularity there, right? So it explodes. So we need to regulate things, things diverge. And that's actually the reason why we get a negative area. Okay? But that's actually also the reason why we get an interesting problem, because suppose you pose the same problem, but this is R5, right? Or let's say this is R2, and then the third direction is just R3. So it's us right now. So this is my plane. I give you a circle. Give me the surface that has the minimal area in R3. What is it? It's the coin, right?
But if the circle is defined, the minimal area would be just this.
Yes. So if this is fixed, and then I could do something like that, I could go up, I could do this, all of that adds area compared to the one that's flat. Do you guys agree? So the coin is the minimal area. That's because the ambient space is R3. But notice that this space is not R3. Actually, you see there's a divergence there. So that means the closer I get to z equal to 0, volumes and areas become larger and larger. Because so what does the string want to do in order to minimize area? It wants to go down. It doesn't make sense in R3, but it makes sense in this geometry. The string wants to get away from the boundary so that this factor is smaller, okay? And then eventually, it doesn't pay off to go further down, and there's a critical point where the string ends, right? So that's the interesting part about ADS. Anyway, so you need to buy this metric. And then the other part I want to do, and I'm sorry, I forgot the radius there. So I told you ADS 5 versus 5 had a radius, L squared. When I gave you the dictionary at the beginning, the radius is of course in front there. And then the string has an action, just like the particle. The particle has an action, and its action is equal to the length of the world line that it traces in the target space or in the space-time. Same for a string. The string now is some elongated thing. As it evolves, it traces a sheet, right? A surface that we call the world sheet. And that world sheet has an area, and the action for the string is the area of the world sheet. Okay? So this will be the square root of the determinant of the induced metric. So this you might not know, but how do you compute the area of the sphere? The 4 pi. Where does the 4 pi come from?
You integrate over the angles.
You integrate theta from 0 to pi, phi from 0 to 2 pi, and what do you put in? So d theta d phi? Sine theta. Where does that sine theta come from? Jacobian of what?
The volume
Of the coordinate transformation from Cartesian to right. That's one way to see it. The other way to see it is that that is the determinant, or the square root of the determinant of the metric on the sphere. So the metric on the sphere is a 2 by 2 matrix, which has component 1, 0, 0, sine squared theta. Right? The determinant of that is sine squared theta, the square root is sine theta. Right? So that's how you compute areas and volumes. It's the determinant, the square root of the determinant of the metric, the object that you use to measure length, on the surface. So this will be exactly the same, except that the metric that I have to use is not this one, because this is an ambient metric, but it's what we call the induced metric. So I have an ambient space, and I put a surface here, and then the surface inherits a metric from the ambient space. It's actually how you computed the metric on the sphere. The metric on the sphere, you started from dx squared plus dy squared plus dz squared, and you plugged in x as a function of theta and phi, y as a function of theta and phi, z as a function of theta and phi, and it gave you d theta squared plus sine squared d phi squared. That's what we call the induced metric, because we started in R3, ended in S2. So this is the same. We start in ADS5, put a string with its own worksheet, and it'll have an induced metric. And it's that metric that I have to compute the determinant of. Square root, integrate, that's the area of the worksheet. Does that make sense? Right? Okay. So I need to do this. This, by the way, is what's called the string tension. It's like the mass for a point particle. Remember, the action for a relativistic particle is minus m, the integral over the proper time, right? This is the same. But instead of m, it's called t, because it has units of energy over length, not energy, or action over length, right? So it's called the tension. And alpha prime is the inverse of the tension, right? But this sets basically the units. This is the same alpha prime that I wrote at the beginning. Anyways, with that introduction, I think I'm going to finish, actually. Or not. What is the... Now we're going to have to write an ansatz for the string worksheet. So what's the ansatz? I erased it, but let's try to describe a surface with that shape, right? So this is the coordinate z, and this is R4. So the obvious thing is that I'm going to put polar coordinates in R4. Actually, because it's a circle, I can just work in R2. And forget there's other two directions, but my curve lives on a plane. Right? So there's two directions in R4 that I can just forget about them. Okay? So let's say x and y. Right? This is where my circle is. The obvious thing is I'm going to put polar coordinates there. Right? So then my metric, my ambient metric, will be this. So I'll have dz squared, but then instead of putting dx squared plus dy squared plus dw squared plus dv squared, I will put plus d rho squared plus rho squared d phi squared plus two more things, right? Two directions that I'm going to neglect because they're going to be constant. Okay, so now what's the reasonable ansatz we can write here? How do we describe this surface? How do you describe the sphere? X as a function of theta and phi, y as a function of theta and phi, z as a function of theta and phi, and r as a function of theta and phi. What's the function of theta and phi? What's r as a function of theta and phi? For the sphere? Constant. That's a surface. R constant in spherical coordinates. Do you agree? So I need to specify all the coordinates in terms of some parameters that in this case are theta and phi, or I could do one coordinate in terms of the others, right? So I could equally well describe the sphere by saying z equals square root of 1 minus x squared minus y squared. That's also a sphere. It's just a sphere in different coordinates. So with that in mind, what's the answer? What are we trying to do here? Well, one thing I'm going to do is that I'm going to identify one of the coordinates on the worksheet with the angle phi. I can always do that, right? So I will say that as I move in this direction in my worksheet, that is equivalent as moving in the phi coordinate in the target space, in the ambient space. Okay? And then in order to preserve this phi symmetry, I will write z as a function of rho. Okay? Make sure this is correct. Yes. So we parameterize the surface with sigma 1 is rho and sigma 2 is phi. So the sigmas are these two coordinates that I put in the worksheet. So in the sphere it would be theta and phi. Okay? And then z is some function of rho. I could write z as a function of phi or rho and phi as well, but that would be weird. Because I don't expect the surface, the minimal surface, to do that. Right? I expect the minimal surface to have symmetry in phi. Maybe it's wrong, but that's the whole point of an ansatz, is to simplify things and see if it works. Okay, so then, having done that, what is the induced metric? So this is the same as what you did for the sphere. Dx squared plus dy squared plus dz squared. Plug in theta and phi, and you get what you get. This is the same. This is the ambient space, or this metric, and I'm going to plug in this. So what do I get? I get 1 over z squared, which is now a function of rho. So z is no longer a coordinate, it's some function of rho, times 1 plus z prime squared d rho squared. So the 1 comes from this term, and the z prime squared comes from this term. Right? So dz is z prime times d rho, plus rho squared d phi squared. Okay? Now I know where to bring down, so you guys can keep looking at that. Good. This is a two-dimensional metric now. So the ambient space is five-dimensional, but the surface is two-dimensional. So this is a two-dimensional surface. What's the metric in matrix form? Well, this will be 1 over z squared, 1 plus z squared, 0, 0, rho squared. Actually, I keep forgetting the factor of L squared, which is important because L squared divided by alpha prime was lambda, square root lambda. And we want to get the square root lambda from the Wilson loop. So it's important that I keep it there. So what's the determinant? Well, okay, L to the fourth, Z to the fourth, 1 plus Z squared, rho squared. Right? So what's my action? This will be. So notice now, what goes in the action is the square root of this guy. So there will be a factor of L squared that comes out of the action, right? So you get L squared, 2 pi alpha prime. It was there from the beginning. That was the string tension. The L squared came out. Now I get d rho d phi, because I chose my coordinates so that they coincided with rho phi, times rho times square root of 1 plus z prime squared divided by z squared. Right? You tell me if I'm making a mistake, because I'm not looking at my notes at this point. Good. Now, notice that nothing depends on phi. So the integral over phi just gives you a factor of 2 pi. So this is just L squared over alpha prime, and then you get the integral over d rho And I get rho square root 1 plus z prime squared divided by z squared. And now I need to minimize this action. Okay? What are the Euler-Lagrange equations? Okay, well, I will get the derivative of this guy with respect to z prime, right? This will be rho divided by z squared, square root 1 plus z squared, z prime squared, and z prime here. All of that prime, right? And then this is equal to the derivative of this guy with respect to z. So I get minus rho square root 1 plus z squared divided by, let's get 2 here, z cubed. That's my Euler-Lagrange problem. So originally it was a two-dimensional problem because it's a surface, but because the ansatz is so simple, it reduced to a one-dimensional problem, like the type of problems you study in your classical mechanics when you learn Lagrangian mechanics. This is what you learn. Instead of prime, you call it dot, right? And usually you don't get such a complicated quote-unquote kinetic term, right? You get x dot squared or whatever, but mathematically it's the same. So now I'm going to give you the answer, the solution, okay? One solution is very, very complicated, but the other one rho equals 0, so let's not forget the picture here. That's the surface we're describing. Rho is the radial direction, and the surface should be smooth when I close rho equal to 0. So rho equal to 0 should be this point here, right? That's the center of my polar coordinates. So that's rho. And then that's 5. Okay, so rho equals 0 is that point in the surface. So I expect the surface to be smooth. Okay, and you can show that one of the solutions to this equation is singular at rho equals 0. The other one is this. Very simple. Okay, this is quite messy when you take this derivative. It has to act on rho, has to act on z prime, has to act on z squared, and then the square root again. This is like 5 or 6 terms on the left-hand side. Okay, and then the right-hand side is simple. It turns out that one of the solutions is very simple, and it's that. So you can just plug that into mathematics. Now, where C, of course, is an integration constant.
When rho is 1, 0, 0.
No, C is an integration constant.
Z.
No. That's why I call this Z.
Z. When rho is 1.
No, when rho is C,
When rho is C.
Z is 0.
So C is the radius of the circle.
So Osvaldo stole my punchline. How do we fix the integration constant C? Well, precisely, you want this rho has to be equal to the radius of the circle when the surface reaches the boundary. Does that make sense? So this direction is z. And this guy is z equals 0. Well, when z equals 0, the radial coordinate, the surface, is at the circle. It pinches the circle. So that's the radius of the Wilson loop. Okay, I never told you what the radius was. Why? It's going to disappear. Why? Conformal invariance. Okay, rescaling things by R is a conformal transformation, and that's a nice conformal transformation. So that actually is a symmetry of the theory. So the answer should not depend on R. Okay, good. Actually, you can describe this surface as it's the same, right? This and this. And of course, rho cannot be bigger than R, because then I get a negative thing inside the square root, but that's perfectly fine because at rho equals R, I already reached the boundary. Also, rho cannot be infinitely large. Sorry. Yes, rho cannot be infinitely large, and Z, you notice, has a minimum value, or a maximum value, right? Which is rho equal to 0, which is this point. So the surface goes down, it moves away from the boundary because it wants to avoid the divergence, but then as the further it goes down, it's adding more and more surface, so it doesn't pay off anymore to keep going down, and then there's a critical value which is rho equal to 0. Okay. So the induced metric, I could just plug in the solution in here. So this was the prime, and you will get a metric, but it's convenient to define so I'm going to write rho equals R hyperbolic tangent of eta. That's a nice coordinate because rho goes from 0 to capital R, right? So by this change of coordinates, now eta will go from 0, so rho is equal to 0, but for rho to be equal to R, the tangent has to be equal to 1, and that's eta going to infinity, right? So this is, and then what you get is that the induced metric is d eta squared plus sinh squared eta d phi squared. It simplifies a lot. So remember, I had 1 over z squared. I had 1 plus z squared d rho squared plus rho squared d phi squared. When you plug in this change of variables, and with this solution, then this becomes z. So the solution now in the new coordinate looks like that, and you plug it in, and the R disappears. And the R disappears for a very simple reason. There was a 1 over z squared, and then you had things that were squared in the numerator. So if you multiply everything by a constant, that constant will disappear. So the induced metric does not depend on R. How do you spell disappear? Am I missing an S? Or do I have an extra P? All right, so I guess I'll just finish. What is the area now? So the area is just plug in this in here and compute. Oh, by the way, this is...
Professor,
Yes?
before you raise that, my question is about the C constant. You see that it's the radius of the Wilson loop,
Yes.
and you take the circle because it's the most simple example.
No, it's because the one we computed before.
But
It's
if
this-
you take a kind of strange curve, which the radius is not constant.
No. A curve
is
It doesn't have a radius in general. The only curve that has a radius is the circle. I don't get your...
I mean a closed loop.
A closed loop that is not a circle, all of this goes out the window. I could, so you're thinking, if my surface is this,
Yeah.
then the surface will be very complicated. And the solution will not be so easy. And actually, what is the radius of this curve? It doesn't have a radius.
Because we have this.
If I pose this problem will also have an Euler-Lagrange equation problem, but it'll be a lot more complicated, but it'll still have two solutions, yes. So two integration constants. Trust me, the integration constants will not be interpreted as the radius of anything, because there's no radius here. The only curve that has a radius is the circle, by definition. So this is the only one that has, this is R. I guess you're confused with the radial coordinate, rho. No, I could put polar coordinates, that's fine. It wouldn't make much sense to put polar coordinates to describe a curve like that. You can always use polar coordinates, it's no problem. All right. Yes?
Sorry, I didn't understand why the solution that you wrote isn't regular in radical zero.
No. I didn't write that one. I wrote the one that is regular at radical zero.
Okay.
Because that's the one I want. Something that, so there's another solution that, can, or yes, explode.
That
Yes.
is that you
Something
show
like that.
there's only one is regular and the other one is.
Yes, it's a second order differential equation, so there's two solutions. My claim is that one solution is actually very ugly, complicated, but fortunately, it's not the one I want because it doesn't behave well at rho equals 0. And the other one is the simple one. So the other solution probably has some singularity. So as you go, rho goes through the origin. This surface, instead of closing nicely here, it probably has some throat and goes to infinity or whatever, explodes. So the one that I want is this one. And that's the one I wrote. I didn't write the other one. All right, so this is ADS 2. Okay. It's ADS 2 in different coordinates than I wrote the ADS 5. So the ADS 5 I wrote this 1 over z squared, and then I had dz squared, or d, yes, and then dx squared. And in that case the x was 4-dimensional, but if I put the x to be 1-dimensional, that's ADS 2, 2-dimensional, it's ADS, etc. Those are point correct coordinates. Now I found the same space, but in different coordinates, and you have to trust me, this is the same space. This is ADS 2, but in what are called global coordinate space. That's actually, don't tell the mathematicians, because they call this the hyperbolic space. And actually they call this the disk hyperbolic space. So this has the topology of a disk. Anyways, all right, what is the area? So remember we had L squared over alpha prime, and then I could plug in the solution here and compute z prime and blah blah blah, but I know a little bit of geometry, I know coordinate transformations, I know, so I can just compute the area now in these coordinates. Now that I know the solution, just compute the determinant of this metric, square root, and that's it. So I'll still get a factor of 2 pi, etc., and then we'll get the integral from 0 to infinity now, because eta goes from 0 to infinity in order to cover the entire worksheet. So eta would be a coordinate that goes like that. This is eta equals 0, and then that's eta equals infinity. And then the eta. And then the square root of that will be do you agree? So this is like, actually, it's not a coincidence that this is a sec of eta. If this wasn't hyperbolic, that would be a sphere. Right? So the sphere is the same. We call it theta, and it's trigonometric sign, not the hyperbolic sign. Right? But this is the same. But of course, the sphere is compact, has finite area. This guy, infinite area. So what is the primitive of sinh? Cosh. So I get cosh of infinity minus 1. It's not a surprise. I anticipated that the area would be infinite because the surface stretches all the way up to the boundary and the metric just explodes at the boundary. So any lengths, volumes, or areas that I compute close to the boundary will be infinite. What's nice is that there's a very good reason, I'm not going to be able to do this, but you're going to have to trust me to just kill this term. Okay? I know what it feels like. Trust me, I know what it feels like. It took me years to accept this fact. Okay? Now, but let me try to explain a little bit how this comes about. When you solve the Euler-Lagrange equations, it's a local differential equation. So the differential equation doesn't really know much about what's fixed at the boundary, what's your variational problem. It doesn't really know anything about that. But this is not just solving the Euler-Lagrange problem. It's finding the surface and then computing the area of the surface. And the area of the surface was the action that we started with. So what's happening is that we're evaluating the wrong area. It's the wrong action. Okay? Because we started just with the integral of the square root of the determinant of the induced metric. That's the wrong action because if I vary it, if I take variations, right, I will get the Euler-Lagrange term, and then I will get a boundary term. Remember that? That's standard in variational calculus. So you get the Euler-Lagrange term, and then a boundary term. Well, that boundary term has to be 0 also in your problem. Otherwise, you're not extremizing the correct functional. Now, what they taught you in classical mechanics is that the variational problem is that in which the curve is fixed at the endpoints, right? So all the curves that I'm considering have the same fixed points. So because it's a boundary term that is evaluated here and here, variations are 0 here. Now this is slightly different. Okay, what I'm fixing here is the value of a coordinate of ADS 5, right? So I'm saying Z goes to 0, rho goes to large R, etc. And because the metric is divergent, posing that problem is subtle. I need to be more careful about this. So I need to write an asymptotic expansion for my solution, close to Z equal to 0, and then see how the solution scales with different powers of Z, and then fix the coefficients in front of that. It's a lot more subtle. It's not just saying, oh, you know, this is a Dirichlet problem where the value of the function is fixed at the boundary, which is, I don't know, when you solve the Laplace equation in electrostatics, right? They give you a bunch of conductors, and you solve Laplace equal to 0, and then you put phi equals to 0 at some surface, or phi equals 4 at the surface, or even phi is some function that you specify by your boundary conditions. That's a well-posed problem in flat space, but in this ADS space, it's not so easy to say that phi is fixed at the boundary. No, the boundary doesn't really exist because there's a divergence there. So you need to write what is the correct asymptotic expansion, blah, blah, blah. And when you do that, you realize that the action that you started with is not stationary if you fix what you want to fix. Okay, so it's the Euler-Lagrange term, which is 0 because you're plugging in the solution, but then there's a term that survives at the boundary. And you need to get rid of that. Because you want the variation of the action to be exactly 0. So in order to get rid of that, you need to add to the original action another boundary terms that will cancel that. And that is divergent as well. Okay? So that is, you will add that divergence, but for good reasons. You add a term that's infinite as well, but you're adding it for good reasons, so you're allowed. And that term is exactly the one that cancels that. Okay? So this is just minus L squared over alpha prime. And now I go back to the first entry of the dictionary. What was the relation between the coupling constants of n equals 4 superbearing mills and the radius of ADS? I think I wrote it here. I think I wrote it here. So that's part of the dictionary. The parameters on one side are identified with the parameters on the other. So this combination, L squared over alpha prime, is just a square root of this. Right? And importantly, it has a minus sign. So now what is the on-shell action? Now I finish. So what is the this is e to the minus s Nambugoto shell, and this is e to the square root lambda. And this is exactly the same answer we got from the Bessel function. Okay? I was expecting an applause. Anyways, I'll just leave it there because I think we're done. So, thank you.
Thank you, Professor. Thank you everyone for staying to the last and a gift from the.
Thank you. Alcohol, I don't drink alcohol. Thank you. And of course.
It's need a hit for work.
Okay, and then some stickers as well. All with the GravUC logo. Thank you guys and congratulations for organizing this. It's great work. Questions afterwards? Outside?
We have
How do you get the corrections?
The corrections? Good. So there's two things. So if you remember, the result from the gauge theory, so using the magic wand, was I think 2 over pi. It was a lambda to the minus 3/4, and then we got this. Okay. Using holography, we managed to reproduce this guy. Well, that's fine. That's the leading one. When lambda is large, this dominates over this. The other way to see it is that this is e to the square root lambda minus 3/4 log lambda, and then plus 1/2 of log of 2 over pi. Right? But when lambda is large, this is bigger than this. So that's fine. So we got the right answer. This is very complicated. This is topological, has to do with zero modes and things like that. Now, you disagree?
There should be a simple way to argue that's that.
The current answer is a paper by, I don't remember if it's Arembo or Cycling,
How old is it?
2019, 2020,
Okay.
2019, where they interpret this as 3 zero modes that appear in the, you will know this, but maybe other people won't, but remember, there are the latitude Wilson loops, right, which are 1/4. I mentioned them at some point in the lecture, right, so you have this parameter. What they do is they compute this. Okay? They do that. So this is what we did now. But then this guy is special. because precisely for that value of theta 0, you get 3 normalizable zero modes in the fluctuations. So this actually goes to Osvaldo's question. So what you would do is you would wiggle this to quadratic order and compute the path integral, right? But, and now going back to Breno's question, when you put theta 0 equal to pi over 2, one of the wiggles becomes a zero mode. So its eigenvalue is 0. So you need to treat it separately, right? So you need to do this collective coordinate business for zero modes. And that contributes, each zero mode contributes with a factor of lambda to the 1/4, because your h bar in if you were doing WKB, etc., is 1 over square root lambda, right? And if you remember, each zero mode contributes with the square root of h bar. So that's lambda to the 1/4, and you get 3 of them. But I know, look, that's the,
It should be a simpler way.
people, I think it had to do with the 3 conformal killing vectors of ADS2, but I think that didn't work. So, anyways, but just to finish with Osvaldo's question, yes, when you wiggle, you would be computing the lambda to the 0 correction, right? Just like in quantum mechanics, the first one is 1 over h bar, and then it's h bar to the 0, and then h bar. Okay.